Robopapa.
Hey YouTubers, today's episode we're going to show you how to use ATTiny 84 and a couple of shift registers to basically run a clock using the interrupts within the ATTiny 84. The shift registers themselves will turn on and off the LEDs that corresponds with the hours or the minutes, and the interrupt will count the seconds that pass, and then every 60 seconds will turn on another LED of the minutes. We also use the other GPIOs for the buttons to set up the current time, and we'll save the current time in the EEPROM. So let's get started. So over here I have basically what we're going to do in today's episode. The minutes will actually, instead of running 59 LEDs, we'll use actually a binary representation. And you can see over here, this is how 59 minutes will look like. Every one will be an LED that will be turned on, and the 0 will be an LED that it's turned off. So instead of 59 LEDs, now we need only 6 LEDs. As far as the hours, we'll just represent that as regular hours. So we'll have 12 LEDs in this. And as I said, for the brain itself, we'll use the ATTiny 84, which is 14 pin AVR. We have one pin for the ground, one pin for the power, one pin for the reset, which leaves us with 11 IO pins. To run the seconds, we'll use the 16-bit comparison interrupt that will rise every second, and then we'll have a counter for the seconds, which then in turn will turn on or increment the minutes, and then increments the hours. We will use a couple of shift output registers, the 8-bit output shift registers. To be more specific, it's the 595 shift register. I will post a link to my video to show how to use it down in the description, and as well as over here right now in the title. We'll use one for the minutes because really we only need 6 of them, and the shift register has 8 outputs, and we will need 2 for the hours because we have 12 LEDs that we need. And then the rest of the GPIOs from the ATTiny we'll use to mark the clock that we want to set it for the current time. We'll have a plus and a minus to increment and decrement, and then like buttons for the hours and the minutes. So all of these will be buttons, the plus minus, hours, minutes, and then the set, I'm thinking that I will have actually a switch. And then of course we will design a 3D casing for it. So I set up a small example over here. I have the UNO over here just as the programmer that will program our ATTiny 84. And what I did over here is we have the ATTiny 84, and it's connected through the GPIOs over here to 2 shift registers with the latch, the clock, and the data lines. So it's the blue, green, yellow, and then we'll have a blue, green, yellow underneath this to go to the second one. And then I connected this one to the interrupt that actually can simulate a second. So it will turn on after 1 second, and then turn off for the next second, and then turn on and then off. So every blink is actually 2 seconds. And then I have the red LEDs over here that will simulate our binary minutes, and then I have an LED over here, 2 LEDs that will simulate the hours, but it also will be kind of like in a binary. That way we can actually see something. And then, like I said, those are the shift register with the enabling and the clear masters to the right, low or high, because we're not controlling that. So let me turn it on, and I set it up that every 2 seconds it will count as if it was a minute, and then every 2 minutes or 3 minutes it will count as if it was an hour. So if we start it up, So we'll see the LEDs over here blinking, and here like the shifting every 2 seconds, and now there will be an hour, and then blink, blink, and then here's another 3 minutes, and then we'll turn to an hour. So that's basically just simulating for us that the interrupts, how to work with the interrupts, how to work with the shift registers. That way, before we actually getting into the soldering and the casing, we know that in a way this one is actually working. So I used only one pin over here for the simulating the blink, but then the rest of them are really just shift registers. So I can have 6 over here, or as many as I want, because the shift itself is you can add to it because of the Q tick itself. So let's look at the code right now and see how we actually made all of this work. So here we are, we're having the code that basically is doing what we saw, that every 2 seconds is counting as a minute, then every 3 minutes will count as an hour. So we're starting with including the interrupts, and we're having the ticks, the minutes, and the hours that's just going to increment. The blinking one that goes from the interrupt, I put it on pin 10 of the ATTiny 84, and then I set up the data, the latch, and the clock for the hours, and then the data, the latch, and the clock for the minutes. This is just like something that I can turn on and off every interrupt itself. And then in the setup, I set up all the GPIOs to output, the one that I needed. Ignore this comment. I just started with the blink sketch example. I set up the no interrupts. Then I clearing the shift registers, and I set up the interrupt itself to use the 16-bit. This is why I'm using the 1 over here, and into the CTC mode. And I'm going to take I believe it was the 64 prescale, and this is the value that I actually needs to compare to. And then I'm enabling the interrupts themselves after I set up everything. The ISR interrupt function is actually for the comparison. So every time that it will match this, and that's why I decided to I had to go with the 16 bits. That way I don't need to have the comparison as well as the overflow. It just can compare this one. And I didn't need a delay, so I could actually use the 16-bit one. And every time that it's actually have an interrupt, I'm setting it up to 0. That way I can start again with the count. I'm putting the level, which is just over here, to the opposite, so the negation of it. So when it was low, it will become high. When it's high, it will come low. And then that LED that actually turned on and off, that's how it does it. I'm counting the ticks, and then if we have 2 ticks, that means that it's 1 minute. If the minute is greater than 3, then we'll set it up to 0, and we're incrementing the hours. If the hours are greater than 3, we're setting up to 0, and then we're sending those hours and minutes to the shift register. And all it does is it's just a couple of functions over here. The send minutes takes the data with the corresponding GPIOs for the clock, the data, and the latch. And the hours is taking the same thing just for the hours one. And then this function is the one that actually pushing all the data. We're setting the latch to low. We're starting from the highest bit over here, and we're decrementing it to 0. We're getting the value itself if it's a true or false. Then we're setting the clock to low, pushing the data in, and then setting the clock high. That will push the data and shift everything as it needed. When this loop is ended, we'll actually push the latch to high, which means it will push everything into the GPIOs themselves. And that's how we see all the pins or the LEDs turning on and off correspondingly. So the next step will be to design the custom board with the ATTiny 84 and 3 shift registers, one for the minutes and two for the hours. So I'll go ahead and start with that, and I'll show as I progress. Okay, wanted to show you guys how it looks like after wiring everything. So the orange wires are actually for the binary minutes, while the green ones are for the 12 hours that we have. Over here we have the switch to make it run or set, then the power supply or the power input over here, then over here on the back that's the voltage regulator, and you can see over here that all the LEDs are connected together. I have my power bench right now supplying the power. In the back over here we'll have the shift registers as well as the buttons and the ATTiny 84, and then you can actually see that it's running right now. It's on 15 seconds increments, or 10 seconds increments. That way you can see that actually moving, and it starts from the bottom for the minutes, then it'll go up as it goes, and then the hours will increment as well. So I'm going to close it off, that way we can see that in action. Alright, so let's take a look over here on the code that actually runs the clock itself. I divided that into two tabs. One is the main functionality, which including the setup and the loop itself, and then the other one is just functions. So we start by actually including the EEPROM and all the interrupts. Then we're creating some volatile variables, that way we can actually access them from the interrupt itself, and we'll take a look in the interrupt function in a minute. So the ticks is basically our seconds, and then we have the minutes and the hours. We have the address for the minutes EEPROM, which is will be on 1 byte, and then the hours as the EEPROM. We can see this one is a byte, then this one is a byte, because really we don't need more than 8 bits to hold the numbers of hours or minutes. Then we getting into if the button for the clock to set it or not, and if we try to disable the interrupts or not. Here's all the hours data latch and clock that goes from the ATTiny 84 to the shift register, and then this one is the same thing as for the minutes. The buttons, so those are with the white wires that I showed you guys before. So the 6, 7, 8, 9, and 10. In the setup itself, we're just doing the normal setup with all the buttons, and then we try to read the memory to see if we have something already in the EEPROM. Disabling the interrupts, setting up everything, that way it will run every second. The interrupt will run every second, then we're enabling those interrupts. Within the loop, we actually reading the set button to see if we need to set up the clock or not. If the clock doesn't need to be set, so that means it's on low, but we disable the interrupt. So if you imagine that we did push the button to set the clock, and we start changing it, we're disabling the interrupts. So that will be the end of it. We push the button to be on the enable side, or to run side, and we still disable the interrupts. So we will want to mark the disable interrupts as false, that way the interrupts will run, and we're writing into the memory, and I'll show that inside those functions over here. And then we're pushing the minutes and the hours with the values that we actually set up. If the clock is actually on the set, but we didn't disable the interrupt, so that's just when we're pushing the push button to be on the set and not the run, we want to disable the interrupts. And this is just for me to set it up for the hour 12. That way I know that it's ready to be set. Then we're trying to read if we pressing the minutes button And then if we're pressing the minutes button, we'll try to see are we doing the plus or the minus. And if it's the plus, it will increment. The minus, it will decrement. Then we validate and push the time, and I'll show you that function in a minute. Similar things we're doing with the hours, except that for the hours we don't need to push the minutes in it. We just need to push the hours, so we're validating the time and then we set the hours. And if we have the set clock, we will delay for 250 milliseconds. So that's basically the heart of it, and then we'll go into the functions to look on how the interrupts and everything else is actually working. So the interrupts is just like a comparison interrupt. If we are not in disable mode, so the push button was not pushed to set and it's on run, we will actually run that interrupt and we will follow it through. And what we do, we sending the counter to 0 again, we incrementing the ticks, which is our seconds. If they're equal to 60, we're incrementing the minutes. Ticks are going to be equal to 0, and then we validate and push the time. So validate and push time, it's really calling this validate time, which really looking to see that we are in our boundaries. If the minutes are greater than 59, we'll set it to 0 and increment the hours. The minutes are less than 0, we will set it to 59 and we'll decrement the hours. As far as the hours, it's just greater than 12 then 1, less than 1, then it will be 12, because it's a AM PM kind of clock. And then, like I said, we validate this time and then we'll push the minutes into the shift registers, which all it does is over here is calling one method, which is shift, and then it passes the pins that it needs, the data, and then how many actually bits it needs to run, because the minutes are binary, so we only need 0 to 5, and while the hours are 12, it's a regular, not a binary, so we need 12, the value 12, so it's 0 to 11. Within the hours, depends on how you're wiring your shift registers. You might need to change this, but for me it's pushing that 1 depending on what is your data. So if it's 12, it will push it to the left 11 spaces. That way it gets to the most significant bit, and then when you are on 1, it will be the least significant bit. And the shift itself is fairly simple. All we do is we're making the latch, which once again we're passing in from these two functions, so it's basically doesn't care if it's an hour or minutes, it's doing the same work. It's pushing the latch to low, then it runs through every bit that we're passing to here, and it's seeing the value of the data. And then if it's high, then it will be high over here. If it's low, it will be low. We're clocking it first to low, and then writing the data, and then we're clocking it high. So that basically pushing one value into the register, but it didn't latch it yet, which means it doesn't push it out of the register. It just start pushing those values in and shifting the previous ones. When we're done with this for loop, that's when we're latching it, which means that it will push it to the LEDs and we'll turn them on and off depending on the values that we set over here. And then just to put a wrapper on the EEPROM, so the read memory and the write memory, let's look on the write memory because it's pretty simple. All we do is an update with the EEPROM address for the minutes and the hours with these values, and remember those are just bytes, so that's why it's 0 and 1 address. And then for the read memory, we're reading them, those 0 and 1 addresses, and we're just making sure that they are still fine and valid, just for sanity check. And that's basically it. You can actually build it. You can see over here it's actually using 24% out of the 8K. It's all using almost 2K and only 37 bytes of the dynamic memory. So that's basically it. Let's see how the clock looks like now that it's closed and everything. So I'll show you that video right now. Alright, so here's the clock when the whole box is actually closed and attached. I'm still connecting through the bench, the power supply, and you can see over here the hours LED, and then the binary minutes are going over here, and then it runs once every minute, and it will increment that. So the next LED will actually be the third one, and then these two will be turned off, which basically will increment the minutes. So that is it, guys. We looked in how we can use the ATTiny 84 with a couple of shift registers to create a clock with the binary minutes and just regular hours. And there we go. Now it's actually shifted. So let me know if you have any questions. Leave a comment below, or even if you have a different idea of how to actually create this project. And as always, don't forget to subscribe. Alright guys, thank you.